So turning point problems. What are turning point problems? So again, we're going to be looking at this quote unquote Schrodinger equation. And the Schrodinger equation for us just means an equation that has this structure. It has no first derivative term. It has only a highest derivative term with a small parameter multiplying that term. The lowest order term is minus q of x, y of x equals, and then equals 0. In the present case, we're going to be interested in the problem on an infinite domain. So x is in the real line. And the only type of boundary conditions that we're going to consider are that y should go to 0 as x approaches plus infinity. And then we just need one other boundary condition to set, it turns out. And the other boundary condition I'm going to pick is somewhere kind of arbitrary. I'm just going to set y of 0 to be equal to 1. And in fact, at the end of the day, this condition, setting this condition isn't so important for us. So I'm not going to talk too much about that. We're really going to focus on applying this boundary condition. So it's this Schrodinger equation with these quote unquote boundary conditions. Now, this one's really a boundary condition, and this one's kind of an infinity condition, if you like. So with turning point problems, we're going to finally address the case where Q changes sign one time on the domain. So the domain is, of course, the whole real line. And let's assume some specific things about Q. Might as well assume that Q is a smooth function. It's the unique place where it's equal to 0. We're going to set that to be at x equals 0. Otherwise, we're going to assume that Q is negative on the negative real line and positive on the positive real line. Now, that means that Q looks a bit like this. Something like that. Of course, now it could dive back down towards the x-axis afterwards. Could get even arbitrarily close to it. But in fact, we're going to not worry about what it looks like in the exterior region, except that we're going to assume that, especially for later on, that, you know, in some domain, this Q is going to be bounded away from 0. Let's make that a different color. And on some domain, let's use purple for this one. Which contains basically most of the negative real axis. Q is bounded away from 0, but it's a negative function. So for this side, let me reiterate. Q is bounded away from 0 and Q is positive. And on this interval, Q is bounded away from 0 and is negative. And then it crosses, meanders up through x equals 0. It has a 0. And then, of course, it's positive thereafter. So I'll raise these assumptions a little bit later as we need them. We're going to assume that basically Q can be written as a times x plus order x squared as x goes to 0. So in this domain, basically Q is just linear as it crosses the x-axis. All right. So this is called the case of Q with a simple turning point. This is the simple turning point case. So we need 3 solution regions. The right-hand side is going to be where Q is going to be strictly positive. There's going to be a left-hand outer solution, and that's an outer solution region. in the same sense that it would have been an outer solution region for matched asymptotics before. In fact, we're going to do pretty much a standard traditional matched asymptotic expansion. Not exactly traditional, but it's going to be it's going to be in a sense that you recognize from our previous work. There's going to be a left-hand outer solution region, and on this interval, we're going to assume that Q is strictly negative and bounded away from zero. And then finally, there's going to be an inner solution region uh, with respect to some stretched variable z, just like usual. Now we're going to have to in this problem, so it's going to break down into three regions. So there's x equals 0. So we're going to have this inner solution region. Then we're also going to have the outer solution region, and let me denote that with a different color. An outer solution region. So this will be the left outer. And this way is the right outer. And then this solution region in here is going to be the inner solution region. Okay, so we're going to have three domains, and they're going to have a tiny bit of overlap, just like usual, so that we can do our matching. So let's start with the right-hand outer solution region. So in that right-hand outer solution region, we know that Q is going to be positive. We're going to assume a little bit more, as I said. So for that right-hand outer solution, we're going to assume that Q is bounded away from 0 by value Q0R, Q naught R. So otherwise, Q is bigger than that on the outer solution region. If this is the case, then we immediately see that our WKB approximation should be of this form. Y of R is equal to some constant over the fourth root of Q. Q is positive. Exponential minus 1 over epsilon integral 0 to x square root of Q dt. Now, you might wonder where's the other solution. The other solution would have been an exponential with the plus sign. So we're going to disregard that right away because that's going to blow up. Only this solution with the minus sign, because Q is positive, this is going to be a positive function of x, and it's a growing positive function of x, as you can see. So as x gets larger, this function value gets larger. So it's an increasing function. So this is minus an increasing function. So this is going to be, of course, decreasing. So this is going to be an exponential, which is going to approach 0. So this is why we only keep the one term, because it's exponentially decaying and the other one would be exponentially growing. So we're going to reject that. So this tells us what the outer solution region or outer solution should be. And basically we're saying, even though it's not written here, is if we expressed our solution, then it's going to be equal to yr of x. I guess I could make this technically a function of epsilon. And this is, we expect to order epsilon. All right, and it has the right boundary conditions. So this is the correct approximation in this right outer solution region. So let's talk about the inner solution region next. To construct the inner solution, we need to do a change a variable, just like we have done before. The only difference here is that we're going to do a simultaneous scaling with a constant to make our equation look and go into a form that is going to turn out to be rather nice. Otherwise, it's pretty much standard. So this z is the stretched variable, and it's has a pretty much standard form x over delta, where delta is a function of epsilon that goes to 0 as epsilon goes to 0. So delta is usually going to be equal to epsilon or epsilon to some positive power. Now, the only difference here is that we are going to tack on this a. And remember, the a parameter, where that comes from is we're assuming that q of x is equal a times x plus order x squared as x goes to 0. So near 0, q is basically a linear function. And it's that a that is appearing in my transformation here. You don't have to include it. You can do a separate transformation afterwards to get rid of that a parameter, which is going to pop up. So we're going to introduce the new new dependent variable. Z is our new independent variable, our stretched variable. And so capital Y is defined through little y, the standard solution, via this change of variables. And as usual, we have to change our ordinary derivatives of y with respect to x into derivatives of capital Y with respect to the new independent variable z. So when you do that, dy dx transforms into, this is a typo here, that should just be a. So a to the alpha over delta and a to the 2 alpha over delta squared, respectively, multiplying the ordinary derivative of capital Y with respect to z and the second derivative of y with respect to z. So those are how the derivatives transform. Now, the equation that we have or are studying is the one that I pointed out on the first slide. It's just this guy here. So that's the thing we're going to transform into the new y variable. Before we do that, if you notice that equation writes as epsilon squared y double prime minus q of x y of x equals 0. I'm going to do an expansion of this q in the new variable z. So q of x is equal to q delta epsilon over a to the alpha times z. Now we're going to think about fixing z and think about an expansion for this as epsilon gets small. If that happens, then delta is going to get small. A is a fixed parameter, so it's not getting small, but this guy is. And so this works out to be, in the transformed coordinates, a to the 1 over alpha. The reason why you get that is because, remember, q is equal to q of x is equal to ax plus order x squared as x goes to 0. So I have an a and a 1 over a to the alpha, and the result is a to the 1 minus alpha. Okay, because instead of having x as my parameter now, then this whole thing becomes my parameter or my variable. And so I get this as my first term from this, and order delta squared because delta is the thing which is getting small now. delta gets small because epsilon is getting small. So the differential equation here transforms into this differential equation just by plugging in my derivative transformation formula and my expansion for cube. So I get a 2 alpha epsilon squared over delta squared, capital Y double prime. This is all my expansion for Q, A, 1 minus alpha delta, Z. Z is an order 1 fixed and finite parameter. Z could be positive or negative because I'm in the inner solution region. Z could be positive or negative. It's both sides of both sides of 0 plus order delta squared, all times Y. And I guess I took this equation, this term, and moved it over to the right-hand side, which is why we get equals here and no minus sign. And all of this is asymptotically correct as epsilon goes to 0. Now we're going to use our method of dominant balance and see if it works. Dominant balance doesn't always work the way you might think it works. And sometimes it just doesn't work. We know that now. In fact, on the second homework, the last problem that you solved, that highly nonlinear problem, method of dominant balance does not work to determine the thickness of the boundary layer. So you have to use other methods to determine that. And so I can say more about that if you come to office hours, or you can ask one of the other students who've worked out the details. Now, for dominant balance, we really only have a couple of choices here. And what we're going to choose to balance is this term and this term. Okay, this times that. And if we do that, that sets a scale for what delta should be. And delta of epsilon works out to epsilon to the 2/3. So we have never seen that before. That's kind of cool. And what we're going to do is we're going to choose the scaling so that basically the A parameter can be divided out here and here. Here and here. So what scaling would we choose then? So what I want to do is I want to choose the scaling so that this power, or this term in A and this term in A, can be the same. That way I can just divide them out. And of course, this term, if I divide or multiply by an A, is going to remain order delta squared because A is a fixed and finite number. So all I want is for A to alpha to balance with A to the 1 minus alpha. So in other words, 2 alpha should be equal to 1 minus alpha. So we get 3 alpha is equal to 1, which produces alpha equals a third. You do the same thing in order to find delta through dominant balance. You balance this term with this term. The only difference is this is not really a dominant balance, balancing A. I'm just balancing it so that I can divide it through and get rid of it. And then there's going to be no A appearing in the equation anymore. So this is the equation after I've divided through by A. There was an A term here and here, divide through by that. Now this is epsilon to the 2/3, epsilon to the 2/3, and this works out to be order delta squared. Delta is 2/3, so this works out to be 4/3. All right. So this is the equation that I have. Let's check to make sure that my term is correct here. So we know that that's an order delta squared. So if so we're checking to see if this term balances with this term. What do we get? So that's epsilon squared over delta squared equal to delta. Right, so that gives us delta cubed is equal to epsilon squared, or delta is equal to epsilon to the 2/3 power. Okay, so yeah, it works out perfectly because now this will give us an epsilon to the 2/3. This is going to be epsilon to the 2/3. And now this has to be epsilon to the 4/3. Okay, so it all checks out. So this is our new inner equation. And we're going to do our usual process of proposing a solution expansion ansatz for the inner solution capital Y. And this one requires a couple of some trial and error to get to work. So it turns out that you're not ever going to get matches unless you use a special form for the inner expansion. And the only way you can find this is to try it and fail. Now, you can hedge your bets and just guess something like this more or less always. And if you do that, it's kind of the safest way to go. We haven't been trying to be so safe previously. Now, let's look at the structure of this. So capital Y, we're saying, is an asymptotic power series in non-integral powers of epsilon. That's because R is just some positive scaling. So RK, R could be like 1/2, and in which case this is half integral powers of epsilon. But it's still not, so that's fine. But this adds another level of, or layer of complexity that is also new and different. So this epsilon to the gamma power, where gamma is any real number, is still going to produce an asymptotic sequence for us. Because remember the requirement whenever we want to produce an asymptotic series, we needed an asymptotic sequence so that when we expanded, we had something like this. And the asymptotic sequence that we used before generically was called phi of k, epsilon. So we needed this sequence, phi k, epsilon, to be what's called an asymptotic sequence. So if you look at what the definition of an asymptotic sequence is, then this sequence here, given by phi k, equals epsilon rk plus gamma, is a perfectly good asymptotic sequence. So this is a perfectly good asymptotic sequence that you could use for asymptotic expansions. It's not your standard integral power series, but it is something like a power series in epsilon. That's perfectly good. Now I'm going to show by choosing or trying to do my matching exactly what this alpha and R should be. So it's going to turn out that the value of R will not matter at all. The value of R won't matter at all. However, you might want to guess that R should be 2/3 because in our in our dominant balance, we found an epsilon to be equal to 2/3. So that has been a guide for us previously whenever you don't have any other terms to suggest what to do. That has been a guide for us to suggest what the power series for the inner solution should be. Now, what we're going to notice is that we really only have two dominant terms here, these two here, and this one kind of goes away. If we really wanted to know what should be the next term for this, we really would need to know what is this term. And so since we're not really interested in that, we're only interested in the leading order approximation, we're not going to care what R should be. We're only going to be worried about what gamma should be. Okay. But this is essentially what we're doing. We're assuming that capital Y has an asymptotic expansion in this weird power series of epsilon. Any questions about that? Okay. Now, regardless of what values we choose for gamma and R, when we plug in our expansion into this equation, we're going to generate the lowest order term, the next order term, etc. The lowest order term is going to be what? So the lowest order term is going to be the order gamma term, okay? Or epsilon to gamma. Guess I could write it like that. The next term that we're going to get, and this should be an equation for y0. The next term that we're going to get is order epsilon plus r. Sorry, epsilon to the gamma plus r. And this will give us an equation, if everything works out, for y1. And then you continue on. The next equation should be order gamma plus 2r. And that should be an equation for y2. But again, we only care about y0. We only care about the leading order expansion, the leading order match. And so it's not going to be relevant for us what are the values of R and what are the functional values or functional forms of y1 and y2. So we plug this into our transformed equation, and the leading order term, which is, as I said, order epsilon to the gamma, is this equation here. So if you are a physics student, you may have seen this equation before, actually, for precisely the reason I'm talking about it today, because it's a differential equation which is important for the study of quantum mechanical systems. Besides that, I don't know of any other applications for Airy's equation, except perhaps for optics. There are a couple of applications in the area of optics, but besides optics and quantum mechanics, I don't know of any. If you know of some or can Google that during lecture, you can let me know.
We use it in our continuum mechanics to material modeling the stress field all the time.
Okay. Okay. Thanks for letting me know. So Airy's differential equation appears in continuum mechanics. That's nice. Now, so this is Airy's equation. And it's one of those equations which is of so much importance that it has its own two important solutions. Airy's function of the first kind and Airy's function of the second kind. One of the homework problems is to approximate this asymptotically for large values of z using a contour integral approach and using the method of, what is it, the saddle point method. So we're going to talk a little bit about that, and that's why those asymptotic approximations of certain functions, including Airy's function, Bessel function, are so important um, in, in asymptotic analysis, because we need them for things like matching or asymptotic behavior of solutions. So these are two linearly independent solutions. This is a linear ordinary differential equation. It's pretty complicated because it has a non-constant coefficient. So the only way you can really attack solutions like this is to do power series expansions, or sometimes you can get lucky and find a closed form solution. This one is not a closed form solution. These Airy functions only exist in terms of complicated integral formulas or power series, etc. So these constants C and D are going to have, we're going to have to wait to determine those through matching. But as I said, these are two linearly independent functions, and here are the plots of those guys. So Airy's function of the first kind is shown in blue. So both of them are oscillatory as you go to minus infinity, and both are exponential as you go to plus infinity. The Airy's equation of the first kind, Airy's function of the first kind, is exponentially decaying, and that of the second kind is exponentially blowing up. But for those of you who have taken physics, what does this sort of picture remind you of? Or in particular, those of you who have taken courses on quantum mechanics. Does this remind you of anything in particular? Okay, well, maybe none of you have taken a course on quantum mechanics, but in quantum mechanics, there's this phenomenon called tunneling through a potential barrier. So if I look at a wave function between two barriers, let's say, so I might have a wave, standing wave like this, and then you have a region tunnels through. It's not a very good drawing, but we're going to discuss this in the next lecture. So Airy's equation, Airy's function of the first kind, is very important for discussing tunneling. So this asymptotic decay is exactly what we need to describe tunneling through a potential barrier. So we're going to talk about that in the last lecture on Tuesday, when we talk about two turning point problems and the Schrodinger equation. So we need to know what is the asymptotic behavior of these two Airy functions, as I mentioned earlier. This is exactly the formula that you're trying to prove with your steepest descent or saddle point method using that contour integral. So you want to obtain either this one term or two terms or an infinite number of terms. By the way, how many of you have gone through that computation? I know one or two of you have and have gotten this term. Have any of you been successful getting a second term in that expansion, or a more? I'm curious to know. Okay, so some of you are still waiting to tackle that one, I guess. And I know a few of you have gotten one term. In fact, I've talked to someone yesterday who got the first term, so that's good to know. But in any case, this is that term. As z goes to infinity, now of course, when you when you look at this problem in the homework, it's lambda going to infinity. and it's exponentially decaying as we expect. The area function of the second kind is exponentially blowing up. So that's indicated by this positive sign here. Now, the areas equations or the areas functions for z going to minus infinity, so that's minus z where z is going to infinity, is going to be an oscillatory solution, a sine wave, with a weak decay, z to the decaying like z to the 1/4. So that's also seen here. Okay, so these guys are decaying, but not too rapidly, only like z to the minus 1/4 power. Okay, and otherwise these are the asymptotic expansions. So this oscillatory behavior is pretty cool. All right, now that's the inner solution region. That's because the Airy equation had those two solutions that have this well-known asymptotic approximation. We've got to try to marry that through matching to the solution on the right hand. But before we do that, we need to construct the left-hand outer solution. So in the left-hand outer solution region, in other words, we're to the left of x equals 0. We're assuming that y is always bounded away from 0 by something we're calling Q0L, which is strictly less than 0. So Q0L bounds Q of x away from 0 on the outer solution region on the left. For this one, we can't disregard or discount either of the two linearly independent solutions that we get from the WKB expansion. And by the way, so the WKB applied for the left-hand region, which we're now in the right-hand outer solution region, but the Airy equation was what determined the solution in the inner solution region. Okay, so we WKB on the right and left, and the inner solution is the Airy functions. In any case, for YL, we're going to have a linear combination of a cosine and sine solution. Remember, Q is negative, so minus Q is going to be positive. Q is negative, so minus Q is going to be positive. So we have E over the fourth root, sorry, of minus Q times cosine 1 over epsilon integral from 0 to x of square root minus Q dt. And the same with the second linearly independent term involving the sine. Only difference is it's a sine instead of cosine. E and F are two real constants that have to be determined via matching, whatever the matching means. So let's examine this integral here. Okay, let's see if this makes sense. So this integral is going from 0 to x, but x is negative. If x was positive, we would be integrating from 0 to x over a positive function. So this would be an increasing positive function as x was larger and larger. But as it is, x is negative. So this whole thing is actually a negative number and actually decreasing negative function of x. Because if we put, well, let's see, not decreasing, it's, what's the right word here? So I think I'm going to mix myself up. So let me just, this statement is correct and true. So let's see, it's negative. Yeah, that's right. So it's negative and it's getting even more negative as x gets more and more negative. Okay, so basically it's looking like this. So for x negative, it's getting more and more negative. Okay, so it actually is increasing. But we only say increasing because we're usually talking about as you move x in that direction. But it's decreasing as I move x more negative. Okay, but it's negative and it's becoming more negative as I make x more negative. So as I go that way, which is exactly what I want because I'm looking at the solution on the left-hand side of this domain. So that should basically function like a cosine or sine does. Okay, so you have to keep that in mind when we do the matching because this function in here, it's a function of x, and it has this shape and form. It's negative and it's becoming more negative as x becomes more negative. Now, let's get down to the hard part, matching the right hand and the inner solutions. So what we're doing is we need to think about this in terms of a picture. I want to do some black ink here. So we have x equals 0. Now our outer solution is going to come down to this regime down here, right? So there's our right outer. And our inner straddles x equals 0 and comes out, and we're going to assume that it comes out far enough that there's some overlapping region. So the inner solution should be valid in that direction. There's going to be an overlap region, namely right here, where the inner solution and the outer solution are both applicable, meaningful. And so it's there where we're going to introduce an intermediate variable, W. So we're going to do that in the usual way. W should be equal to x over eta. W is a fixed and finite number, and eta should be above the scale of so remember, this is called the intermediate scale, and this is called the boundary scale. And this guy should be above that boundary scale. We know that one to be epsilon to the 2/3. So this one cannot go to 0 as fast, right? This one has to go to 0 faster. So this one could be something like 1/3, epsilon to the 1/3, but it can't be on par with epsilon to the 2/3. It could be epsilon to the 1/2 power as well. But as usual, we don't actually have to choose that intermediate scale. We just have to know that it's a larger asymptotic number than the delta scale. W is positive, fixed, and finite, order 1 number, as usual. So now we know what our inner solution or our boundary layer scale or what did I call this? The boundary layer variable or the stretch variable z is equal to a to the 1/3 over epsilon to the 2/3 times x. Solving for x, that means that z is equal to a to the 1/3 eta over epsilon to the 2/3 times w. So all I did there was solve for x, right? X is equal to w eta, so just put the w eta there for x. And we're going to perform an n equals 0, m equals 0 match according to our standard procedure. So yeah, Calvin, uh, you're right. This is technically increasing. Yeah, so referring to the chat there. Sorry, I missed that chat. So this is our intermediate variable, and now our inner or our stretch variable could be written in terms of that intermediate variable as well. And we do the usual sort of procedure. We're going to write the inner and outer solution only in the W variable. So that gives us an expression for both of them in this intermediate or matching this overlapping domain, and then we use our usual procedure to find out what is the matching function. So what we're looking for, now I'm not going to be so specific about saying that this should be little o of epsilon or whatever. I'm just going to say, okay, I put in for x w times eta, and I expand, and I'm looking for a function which is asymptotic as epsilon goes to 0 to that function. But it's written only in the terms of the variable w. So that's my goal, to figure out what the heck that should be. All right, well, let's put together some pieces of information that we know. First of all, Q of U is equal to AU plus big O of U squared as U goes to 0. I don't care what U is, it could be anything. As long as it's getting small and I put it in here, then we can use this asymptotic approximation for Q. If you do, so this just involves using the binomial series expansion. If I know this two-term expansion for Q of U, then the square root of Q of U is just going to be the square root of AU plus big O of U to the 3/2 power. So I'll leave it to you to work out those details. I spent a few minutes calculating this by hand using the binomial expansion. Usually it's called the binomial series. Then you dump that into this this integral. We'll call that the capital Q integral. And then you integrate using this this little expansion here, and you find out that you get 2/3 square root of a u to the 3/2 power plus big O of u to the 5/2 power as u gets small. I don't care what u is, whatever it is, as long as it's getting small, then this has to hold true. Now this Q of u, that's the whole business that's involved inside here, right? So minus 1 over epsilon, this can be written as Q of W times eta. Now, so that takes care of this portion here. We only have to take care of this portion, 1 over the 4th root of Q, W eta. And I do that in a similar way. If I know that I have a two-term expansion for Q, I can use a binomial series to show that 1 over the 4th root QU is just 1 over the 4th root of A times U. That's the leading order term, plus a correction term, which is big O of U to the 3/4 power as U goes to 0. Still going to 0 as U goes to 0, no problem. All right. And then what I do is basically I'm going to take these values that I just calculated. So this is the important one here, the important one here. And you plug those in here and here. Only your U is going to be W times eta. And keeping in mind that eta goes to 0 as epsilon goes to 0, that determines that our matching function, this is what I'm calling the 0, 0, R match, is equal to A, that's the undetermined coefficient, 4th root of AW eta. Okay, that's because I'm using this guy with U equals W eta, exponential minus 2/3 epsilon. That's coming from this 2/3 here and the fact that I have a 1 over epsilon there in the first place. square root of A. The U you replace with W eta. So that becomes W to the 3/2, eta to the 3/2. And I'm not going to worry about how big the error terms are, whether they're order epsilon or whatever. I don't care, right? Because I'm doing a very coarse-grained matching, and I'm not really interested in anything which is higher order. So starting with this, do those very simple asymptotic expansions to get those things, and we get this asymptotic approximation. So that's my matching term. That's all I need. This has an undetermined, single undetermined coefficient. Everything else is given. A is given. W is our intermediate variable. Eta is our scale variable. It's going to turn out it's not going to matter what that scale is. Whatever it is, whatever we choose to work will work. And so this is our right-hand matching function. So now we need the corresponding inner matching function. And the way you get that is you take the matching, or you take the inner solution to the lowest order, or to the leading order. In this case, notice that our leading order is y0 times epsilon to the gamma power. Okay, y0 epsilon to the gamma power, because remember that leading order term started with epsilon to the gamma. I don't know what gamma should be. And for that matter, I don't know what R should be, but R is not going to be important for our matching because we're only doing leading order. All right, so I plug in for Z, my formula for Z in terms of eta and W. And then, of course, I have to match, or I have to multiply by epsilon to the gamma because that comes along for the ride. And I want to find a function which is asymptotic to this as epsilon goes to 0 for fixed and finite W. And I want to try to see if that matches this right-hand match function that I just computed. So this one is actually easy because I just used those asymptotic formula that I had for the Airy functions. Let's see, do I have that correct? That is, yeah. So for our Airy functions, right, we had AI and BI. So there's my BI term, there's the AI term. The AI term is asymptotically, or is exponentially decreasing, and the BI is exponentially growing. Otherwise, if you use those asymptotic formula, you get the following. I know immediately that I cannot connect this asymptotically growing formula to anything here. There's no exponential growing term. So immediately I see that D has to be set equal to 0. What about for this term corresponding to the Airy function of the first kind? Well, notice that I'm not allowed to have any power of epsilon in here. There's no power of epsilon here. That's fine because now I'm able to choose my gamma to make this guy epsilon to the 0 power, or order 1. So that's what tells me that I need to select gamma to be equal to minus 1/6 power. All right, now you could, like I said, by trial and error, you can hit upon this, that actually you should start on this function. If you don't put that gamma cushion in, build that gamma cushioning in from the beginning, you'll see eventually that you need it. So you'll have to come back and add it in the end anyway. So I'm just showing you what I learned through this process, that you need this, and so just add it in from the beginning. So this is going to allow me to eliminate any direct epsilon dependence because there's no direct epsilon dependence here. Now, all of these other terms I can match. So here and in down here, I can match all those up. So let's see, we have w to the 3 halves and eta to the 3 halves. I don't have to do any matching there. Okay, square root of a. So all that stuff matches exactly from the beginning. No problem. Everything in the argument matches up. What about down here? All right. In fact, well, I've gotten rid of this by choosing gamma to be equal to minus 1/6. But now I've got c times all this, and all of it is going to be order eta to the 1/4 power, minus 1/4 power. Same with this. This is order eta to the 1/4 power. Everything is looking good. So now all I have to do is I have to match this coefficient and all of this stuff in the basement with all of this stuff. In fact, this is gone, but all the rest of the stuff is there. So let me review those matching conditions on the next page. So to match, I'm going to require that gamma should be minus 1/6, d should be 0, already discussed those, and that these two terms should be equal. A over fourth root of little a w eta should be equal to c over 2 square root pi a to the 1/12 power, eta to the 1/4, w to the 1/4. So you can get cancellation of the w and eta terms, and so all I have to do is equate the other things. Now, what I'm going to do is I'm deciding to keep a as my free parameter. So that means what I'm doing is eliminating a or eliminating c in terms of a. And if you solve for c in terms of a, you get 2 root pi times a over a to the 1/6 power. So the matching function therefore becomes exactly equal to this. Remember, the two matching functions from either the inner side or the right-hand side have to match. And so I'm going their matching function, the inner right. So you remember, I don't know if this is good notation or good use of symbols, mathematical symbols, but at least it's descriptive. And there are a lot of letters there. But, so that's describing the matching function. So it's the matching function on this matching region. So outer solution is that way. Inner solution is this way. So right here is the matching region. So this is where this function, the 0, 0 in our matching function, that's where that guy lives. Now we have to do the same thing on the other side. Match the left hand in the inner solution. Again, you introduce an intermediate variable w. In this case, w should be negative because x is negative. Your eta scale, you should agree to make that positive as usual. And it satisfies a similar sort of scaling. Now, keep in mind, this eta does not have to be the same as the eta that we had on the right-hand side. So I could call this eta left. But that's too much, right? So eta on the right, eta on the left, it doesn't matter. Just recognize that they may not be the same. So again, z could be negative, w can be negative, or is negative actually. And so z is exactly as it was before, but you just keep in mind that w and z are both negative in this case. So the matching that we're doing here is x is equal to 0. The inner solution lives here. Inner solution region. The outer solution, left-hand region, comes all the way down to here. It's outer left, and the overlapping region, matching region, is here. So this is where things like W live and the eta scale lives. So W is somewhere in this region. Let's see. I think that's all we need there. Now, what's the left-hand matching functions? What should that look like? So we do our usual procedure. You replace X with W eta, keeping in mind that X is negative and W eta is negative. And we need to expand these functions, right? So if you do that, then you get similar expansions as before. So for this, for example, here, 1 over the fourth root of Q evaluated W and eta minus Q, because we have to put a minus Q here because Q is now negative. This just becomes minus AW eta. And this is fairly similar to what we had before. Just keep in mind that everything is negative now. So this becomes cosine minus 2/3 epsilon square root of A minus W to the 3/2. So W is negative, so this is now made positive. So I fix that up by adding a negative sign here. Eta is always positive, and you get the same thing for this sign. Now, for our area functions, let's see, am I to the area thing yet? Yeah, so this is my 0, 0 left matching function. Now I need the 0, 0 inner. Okay, and the only way I could do the inner and make sense of it is I added a negative sign here. I think I added a positive sign in the previous one as well. So you replace Z with the expression in terms of W and eta. Of course, I have to tag along epsilon to the gamma, but now I know that gamma is equal to minus 1/6. Already fixed that. And I'm looking for a matching function called y00 in negative, only in terms of W and epsilon, which is asymptotic to that. And I know what the asymptotic formula are from my list earlier. So just go back to one of the earlier slides somewhere in here when we were talking about the area function and the asymptotic representations for those. You get something which looks like that. The problem is now, and now I only have one area function because remember D was equal to 0, so the B's are out of the picture. BI out. I only have to deal with the AIs. So the asymptotic approximation of that was this weird formulation here. So it didn't have the negative like I got previously, and it has a positive 4, a pi over 4. So I have to transform this a little bit. So you're going to use trigonometric formula to do this transformation. First, you do the sine angle addition formula. So you get sine of this angle times cosine of pi over 4. But the cosine of pi over 4 and the sine of pi over 4 are the same. They're just square root of 2 over 2 or just 1 over root 2. So that's where you get this 1 over root 2, which appears. Okay, so no problem there. What do we need to do next? Next, I'm going to introduce a minus sign in here on the sine term. Well, remember, sine is an odd function, so if I introduce a minus sign, I have a minus that. Cosine's an even function, so I can just bring the minus sign in. And now I can do my matching. So matching now, so if you go back, here were my matching functions for the left-hand match. Okay, cosine with minus, blah, 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 sine with minus, blah, 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 and some stuff out front. Now I can do the matching here because I've gotten something which looks similar. These match exactly. I don't have to do anything to those, which is good because there are no free parameters left over there. Uh, so if I had to do matching, I'd be out of luck. A gamma is equal to -1/6, so that goes. And so now I merely have to connect this guy here, the C, with this E and the F. So, of course, I already knew this. I probably don't have to restate this. We already know that. But it should be a confirmation, right? That everything is still making sense. To match those sines and cosine functions, I need to do or have these equations matching. And this tells me ultimately, remember, I'm keeping A as my free parameter and I'm eliminating all other parameters. So this tells me that my E has to be equal to root 2 times A and F has to be minus root 2 times A. And now we're basically done. So in quantum mechanics literature, these are known as the connection formula. And it's not so easy to do because we have these three solution regions. It's not as easy to do the outer solution plus the inner minus the match. That is nice when it works, but here it's not so clear that it's going to actually work. So all we're going to do here is the easiest thing. We're going to write these formula as they would exist in the overlapping or in their not, well, in these regions which do have some sort of modest overlap. So remember in the left-hand region now we've deduced that we have the sine and cosine. Okay, and all we had to do there is figure out what the values of E and the F should be. So we're plugging those in. E was square root 2 times A. F is minus square root of 2 times A. Then we have the Airy solution in the middle, which joins the two things together, this cosine sine, to this exponential, which exists in the right-hand outer region. You can do a little more massaging of this to get it into a form which is only has one term. So if you want to do that and just get a one-term approximation, you can do that. You get the sine of an angle plus pi over 4. And the reason you can do that is you can use the sine angle addition formula. In fact, you can just check that this equals these two terms here. So that's the solution. It's an oscillatory solution in the left-hand region, the Airy function in the intermediate or inner region, and the exponentially decaying solution in the right-hand region. So that connects all of the that connects the two natures of the WKB expansion that we talked about previously, the oscillatory part and the exponential part. In this case, we chose only to do the exponential decreasing because of its connection with quantum mechanics and tunneling, as we'll talk more about momentarily. So these are what are known as the connection formula. Now, you might be wondering, is it possible to come up with one uniformly valid composite solution, composite approximation? It turns out there is, and this is what is known as Langer's uniform approximation or Langer's formula. Langer was a German-American mathematician working in the 30s on quantum mechanics and maybe the 20s as well. So for this single turning point problem, he showed that you can have a single uniform composite expansion which connects all three of these equations together. Okay, so 1, 2, and 3. I'm not going to try to go through this or explain it. Maybe in future iterations of this class, I'll have students derive this and show that, in fact, that in these three regions, you just get these terms, these expansions. The easiest one to show right away is this one, that this is an Airy function because it's basically constructed from an area function. So what remains? The only thing that remains is how do you get rid of this parameter a? Well, we have this final normalization condition, y of 0 equals 1, and that you can use to get rid of a. But we're not going to do that because, in fact, these connection formulas are going to be quite useful to us in the later section where we discuss two turning point problems, and we're going to need that free parameter of a in there. So I'm just going to keep it in there when I write out the connection formula. Otherwise, you can deduce that parameter by this this condition here. In fact, the way you do it is you just plug in 0 for the area function, and you get pretty quickly what a should be if you want to connect it to or have this be your normalization. Are there any questions? So this is the one turning point problem. And so next time we're going to discuss quantum mechanics when you have a potential, which looks something like this, a single well potential. And we have a given energy value. Now, the combination of these two things, the difference of these two functions, this is called the potential V, and this is called the energy or the kinetic energy level E. You can see that if I just reorient my way of thinking, I can think about this as my Q function. So precisely, Q is going to be defined as V of x minus E. If this is E and this is V here, then this Q actually has two turning points, one here where it crosses the x-axis and one here where it crosses the x-axis. So now you can see I have something interesting happening. Roughly speaking, I can develop an asymptotic expansion using WKB for this region and also this region, because those regions, if I just zoom in, look like one turning point problems. So I have a one turning point here, one turning point here. The difference is it's kind of mirror symmetry. So this is the one we just solved. So I have to flip my solution to get this turning point over here. And then I kind of have to stitch them together in this intermediate region. And that's going to give us what's called a quantization condition, which is very important in quantum mechanics. So that's the two turning point problem, which we will get to next time. Any questions? Anything at all? All right. Well, if you don't have any questions or don't want to express those in front of everybody, I would be glad to meet with you in office hour tomorrow or answer any emails that you might have. If you want to stay on and talk to me, I'll hang out for a few minutes and answer any questions that you might have after the class. But otherwise, I'll see you guys on Tuesday. I hope you have a nice weekend. Bye-bye.